Hi, my name is Shane Moore. I'm a technical service representative for PAVCO. First, I want to tell you that I appreciate the opportunity to come speak with you guys today about bulk processing of trivalent electrodeposits. So what exactly are we talking about? It's basically trivalent chromium that can now be plated in a barrel application. So just to get back to give you a little history on chrome plating, back in 1920, Dr. Sargent was working in research and development at Cornell University, and he theorized how chromium plating could possibly work. So then Fink, and he published a paper on this, and Fink and Eldridge built on this paper and were actually the first ones to make it work and to make it go commercially widespread. In the beginning, it was mostly just for car parts and motorcycle parts, things like that. A lot of people think that trivalent chromium is a newer technology, but actually it's been around a pretty long time, since the 1970s is how long it's been, successful. It started before that. It was a chloride-based system, but it wasn't very viable in that you had to have special equipment. It was a darker deposit. You couldn't control it. It's hard to maintain. So it wasn't until the 1970s when chemical manufacturers, they did more research and development and put the work in, and to where we have our chloride and sulfate-based system are available today. So now we have chloride-based, sulfate-based, and then barrel application, which is also sulfate-based. So the bulk processing of chromium has been tried for a very long time. In the beginning, it was only hexavalent chromium, because trivalent wasn't around yet. It was only able to plate small loads, in that it was basically not even a plating barrel. It was like a basket, and you put the small load in there, and then you just kind of crank it down to where all the parts are touching each other and the basket. But the only problem with this was the parts on the outer edge of the circle, or the outer side touching the basket, were plated, but the ones on the inside of the load got very little to no plating at all. So it didn't work very well. Whenever trivalent chromium was introduced in the 60s and 70s, it helped some, but it was still very limited because of the specialized equipment needed, and it just wasn't a very robust system. So there are parts that basically have to be barrel plated, whether it can't have rack marks, it has to have complete coverage down in the low current density areas, and just from a labor standpoint. So these barrel chrome alternatives were invented. And these are different alloys. There's tin nickel, tin cobalt. Tin cobalt is probably one of the most popular. Nickel tungsten and white bronze. The only problem with these, like many alloy baths, is that they're hard to maintain. They're very pH dependent. You can vary the color just a little by, if the pH goes up or down just by a small degree. Especially with the tin-based ones, it generates static tin, and when that happens, then it precipitates out. You have to add it back, and it's more difficult to maintain. So we'll talk about some of the advantages for our trivalent chromium barrel application. Like I said, it eliminates the problems with the non-chrome alternatives. This is actually real chrome. It's depositing chrome on the parts, not a chrome lookalike. It's actual chrome metal. Like I said, the most popular I've seen in the market is tin cobalt. That's the closest to it, but it darkens very quickly after entering a corrosion chamber, salt spray, cast cabinets, whatever. And tin nickel and some of the other alloys have to be complexed, and some of those strong complexes they're difficult to waste treat because they chelate other metals that you're trying to flock out during your waste treatment. So these are some pictures over here that shows the trivalent chromium under a microscope, and then the tin cobalt as well. And actually these parts, we wiped them with a chem wipe, which should be non-scarring. It's not aggressive at all. The trivalent chromium, you can't even tell that it was rubbed, but the tin cobalt is so soft that you can see all the scratches and things in there just from wiping it with just a small chem wipe. So some of the other advantages, of course, the labor, the more racking and unracking parts, you can apply this in a barrel. You can mass produce your. It's about 10% the labor cost of rack chrome, and those are real numbers. Those are we did some studies at some of our installations, and these numbers are from the study. It's about, when you take into account the waste treatment of hexavalent chromium, the air permits that you have to have, the discharge, everything combined, it actually ends up being cheaper than hexavalent chromium. Like I said, there's no rack marks on it. You get complete coverage down in the low current density areas, and you can see that in some of these pictures that it reached the very bottom of the sockets. And it's a much, the thickness distribution from the high current density areas to the low current density areas are much closer than with a rack, with rack plating. And this is another example. We cut one of these parts open, and you can see that all the way down in the very extreme low current density area, we still had plating in there. So it was completely covered from the highs to the lows. So now we'll talk about color. The way this is measured is on a colorimeter. The numbers are, the L, 100 is completely white, 0 is black. The A is blue to green, which doesn't really matter in the case of chromium. But the other important number is the B value, and that's how blue or how yellow the deposit is. So usually the L and the B are the main specifications that customers have to meet, how white it is and how blue it is. So just for comparison, the hexavalent chromium is going to be the whitest and the bluest. So it's 82 to 84 L value, -1 to -1.4 on the B value. The beryl sulfate is really close to, it's not quite as blue as the hexavalent chromium. The sulfate is actually the closest to the hexavalent chromium color. But the beryl sulfate and the chloride trivalent chromium are very, very close in color. So corrosion performance, we ran some studies on this with duplex nickel, single layer nickel, triple, triplex nickel, and quadruple layers, and I got a lot of data from that, and we were able to put together a actually this chart on the next page gives a little more information. Yeah, there we go. So you can see by just having gone from a single to a duplex nickel, you only have to have 12 microns instead of 18 on a single. So having a thinner layer duplex nickel gives you a lot more protection than a thicker single nickel layer. This is because of something called STEP. It's basically a measure of the difference of sulfur co-deposition in the bright nickel layer versus the semi-bright nickel layer. You want to have you want to have a millivolt reading of around 120 to 140, and that gives you your maximum corrosion resistance. Now, if you need the higher numbers like this, then we would have to go with either a triplex or a quad. So all 4 layers would be semi-bright nickel, high sulfur nickel, bright nickel, and then microporous nickel, and then the chrome. So that would be all 4 of those. So we did some more, this is some more data that we got from our study. This is duplex nickel, and we plated them as close as we could to the same thicknesses, so we could do some direct comparison. This is kind of what they look like. You can see the beryl tin cobalt, like I said earlier, it goes dark almost right after you put it into the cabinet, so it's not very corrosion resistant. As far as functionality, it is it's resistant, but as far as the appearance, you can see that the corrosion looks much worse on the tin cobalt than all the others. So just a summation of that, just basically shows they all did really well, or about the same as far as comparison, except for the barrel tin cobalt. We gave it a low rating just because of the appearance. So then we repeated the same test, but this was for cast exposure, and we wanted to see how well that did. So here's the parts after 24 and 48 hours cast, and basically all of this is summarized in the next page. So the chloride trivalent chrome rack and the beryl sulfate trivalent chromium actually did the best, followed by the sulfate and the tin cobalt and the hexavalent chromium. So the beryl sulfate and the chloride did extremely well after 24 and 48 hours of cast exposure. So then we wanted to see what the difference in the hardness was. So we did something called nano indentation. It's a specialized hardness tester. And we did the test, or we sent them out to be tested because we actually don't have the equipment here. So these are the hardness numbers. So the hardest is sulfate trivalent chromium, and that's been proven many times. We've done this test quite a few times, and it always comes back as the hardest. Hexavalent chromium is next. So then you can see the beryl sulfate trivalent chromium is really close in hardness to the chloride trivalent chromium. And we have many customers that use the trivalent chromium on tools, hand tools, and things like that. So it's hard enough to meet that hardness spec. And then the beryl sulfate chrome is just under that. And then of course you can see the tin cobalt beryl is a very soft deposit because it's such a tin rich deposit. So some other comparisons of the different chrome systems. You can see that the chrome metal in the beryl sulfate chromium, well, and all the trivalent is much lower than chromic acid. So you've got a lot less to waste treat. The beryl sulfate actually runs at between 4 and 5 grams per liter, so that makes it a lot easier on waste treatment. pH, the anode type, you have to use the mixed metal oxide coated titanium, just like you do for the rack sulfate bath for the barrel chromium. The chromic acid, of course, has to use lead with some other alloying metals in there, but that creates a pretty dangerous toxic sludge. So you don't have to worry about that with the beryl sulfate system. The covering power, the beryl sulfate chromium completely covers, like we saw in the other slide, all the way down into the lowest recessed area. And then the waste treatment is simple. It's just like it's just like treating a nickel bath. And then then the toxicity, and there's always the risk of chromic acid having whitewash issues. You don't have to worry about that with the beryl chromium or any of the trivalent chromiums actually. It can actually withstand current interruption and still be fine. Very robust system. So then the plating rates are listed here. At first we didn't account for some of the alloying metals that plates out with the beryl sulfate chromium, so we thought that we were having to plate like 30 minutes to be able to get 0.25, 0.3 microns. But then when we did some SEM work, we saw that we were getting like 0.6, 0.7 microns instead of what we're seeing on the X-ray as only 0.2 to 0.3. So now this helped us to determine that we only have to plate between 12 and 14 minutes. So it's not as much as a hurdle anymore to be able to get the required thicknesses. And then these are some of the other rates as well, 6 to 7 minutes for sulfate rack. And then the chloride and hexavalent chromium are about the same, about 2 to 3 minutes to be able to get 0.25 microns. So these are some SEM images of the different deposit types. You can see the chloride trivalent chromium is micropores as plated. The sulfate trivalent beryl is also micropores as plated. So you get, it's almost like having a microporous nickel, but without the microporous nickel. It's the micropores as plated, so you're going to have very good corrosion resistance. Because you can't stop corrosion, you can only control it. So this spreads out the corrosion over many, many different areas instead of concentrating in one area and it going down to the substrate. So what type of equipment do you need? Like we said, you have to have MMO coated titanium anodes. It's a mixed metal oxide, and we have preferred vendors for this. Polypropylene tank because it's only runs at about 110 degrees Fahrenheit. The variable speed barrel is typically just in the beginning until we find out what type rotation speed is best for your application. So then after that, then you can design, the rest of the line for like normal, typical. But so the variable speed is just basically in the beginning. Unless you want to have that, unless you're going to be running a lot of different parts, then it would be really good to have a variable speed barrel on throughout the line. Would be very advantageous. Let's see, some other things. You need mild air, mainly just for when you're making up the tank, when you're making additions. It's just to stir and to have proper mixing of all the chemicals when the additions are made. Let's see, you need to be able to heat up to 60 degrees Celsius. That's mainly in the beginning whenever you're dissolving all the salts. But other than that, it only runs at about 110 degrees Fahrenheit. So that's usually the only time it's needed to go up to 60 is just whenever you're dissolving the salts in the beginning. If you have zinc and copper substrates, copper is the biggest contaminant for this system. It only takes maybe 5 ppm of copper to start getting a darker deposit. So it's best to have ion exchange for this. As soon as as soon as any copper is generated, then it's immediately removed with the ion exchange resin. And the good thing is the resin that we recommend actually is the most specific for copper. So as soon as it goes into solution, the ion exchange resin removes it right away. And then it's very tolerant to nickel and iron, but if you have a lot of like cylinders that don't get plated on the inside and you start building up a lot of iron, then it may be best to have like a dummy tank or just have the capability to put in a dummy for electrolysis just to remove that contamination. Some of the operating parameters, like I said, the chromium is at 4 grams per liter, making it very easy to waste treat. pH 3.6, this is the temperature. I apologize for saying Fahrenheit. It's 43.3 degrees Celsius is the operating temperature. Current density, we run anywhere from 0.5 to 2.1 ASD, 1 to 1.1, 1.2 ASD if possible. If it's larger parts that make and break contact, then usually we want to turn the current down just a little bit. Anode current density needs to be below 5 ASD, so when you're designing the line, you need to keep that in mind because if your anodic current density is over 5 for very long, then you can start generating hexavalent chromium, and that's a big contaminant for this bath. You'll lose, first you'll start losing low current density coverage, and then it'll just completely stop plating altogether. So we want to avoid that. So we've had a lot of success in the field with, we've plated it over bright nickel, over electroless nickel. The production coverage has been phenomenal. All of our customers have said that they get better low current density coverage, no rack marks. You're able to completely cover the entire part, and we've had installations all over the world, and it's a very easy to control. A lot of people ask about that if it's difficult to control, and it is not. There's only there's not very many additives. You can, if you set it up by an automatic feeder, then it runs flawlessly. It's very simple to operate. So for conclusions, like we talked about, it has excellent throwing power, complete coverage down in the low current density area, reduced labor costs, of course, because you'll be able to plate a lot at one time instead of having to rack each part, especially with smaller parts. So improve production. Let's see, this consistent color, as long as you keep all the metals, the metallic contamination is the #1 thing that's going to be detrimental to the color of the deposit. So we want to make sure that we keep it clean, keep all the, especially the copper and the zinc out with ion exchange, dummy out the nickel and the iron, and it works great. So I want to thank you again for allowing me the opportunity to speak with you guys, and I hope everyone has a great day. Thank you.